Here we discuss vorticity dynamics, and really this is just a very short introduction on vorticity, and what we'll start with is just with a number of definitions. And we'll start with the definition of the vorticity. So let's consider a velocity field u. And remember that our velocity here is a velocity field. So we have at every single point x, we have a whole vector. So we have three components. And so for this velocity vector, this velocity field u, we can define another associated vector field, which is called the vorticity field. And this vorticity field is defined as the curl of the velocity. So mathematically we can write that the vorticity field, which we represent with omega, which again is a vector field, is equal to the curl of the velocity field. This here is the curl. So how does this, what are the components of this vorticity field? Well, in Cartesian coordinates is the easiest to compute. So in Cartesian coordinates, we can write the curl omega is equal to the curl, which we write as a pseudo vector with the gradient operator, cross the velocity field. And we can compute this simply by doing this cross product. So the first component will be partial w times partial w partial y min partial v partial z. The second component will be min partial w partial x plus partial u partial z. And the last component is will be here partial v partial x min partial u partial y. So what does one thing which I want to highlight here is that again, as much as the velocity, here the velocity u is a vector field, the vorticity here is also a vector field. Alright, so how does the vorticity field relate to the velocity field? Now, in other words, what does the vorticity field represent? Well, we have briefly discussed the term vorticity, and that was when we looked at how we can decompose a velocity field. So if you remember, when we discussed how we can decompose the velocity, we said that we can write the velocity in the neighborhood of a point x naught as the velocity at x naught plus 1/2, this is a matrix here, 1/2 the gradient of u minus the transpose of the gradient of u times delta x plus 1/2 the gradient plus now the transpose of the gradient of u times delta x. And we discussed that this here we called the rate of strain vector tensor, and that this part here represented the deformation. This here we discussed represented a translation, and this here we called the vorticity tensor, and we said that this here represents a rotation. Okay, so yeah, you can guess we didn't call this for nothing the vorticity tensor. Of course, this vorticity tensor is directly related to the vorticity vector. In fact, if you write this vorticity tensor, right, so if you're writing the components of this tensor, so for instance, you have 0 on the diagonal, and on the first column you will have from this term partial u partial y min partial v partial x, and in the third column you will have partial u partial z min partial w partial x. Right, so let me write this tensor. So if I rewrite this rotation tensor, I have the 1/2. These terms we discussed before, right? So here's the same. I have partial v partial x, this is in the gradient of u tensor, minus partial u partial y, this is minus the transpose of the gradient, and so on. And you recognize here the components of the vorticity vector. Like, let me remind you, the vorticity vector is equal to the following. This is our vorticity vector. It has three components, omega x, omega y, and omega z. And so you recognize here that when you write the vorticity tensor, this component here is minus omega z. This component here is omega y. And this component here is minus omega x. We have zeros on the diagonal, and this tensor is antisymmetric. So here you see that the vorticity tensor, the component of the vorticity tensor, what we call the vorticity tensor, are the components of the vorticity vector, of the vorticity that we have just discussed, which is the curl of the velocity field. Now, another way of seeing directly that this is related to the rotation, so that is, we discussed, is related to the rotation. If you were to write the rotational component of the velocity field, so we wrote it previously, we wrote it omega dot delta x. So if you do the matrix product of this omega dot delta x, you see that you could also write it as 1/2 of omega, the vorticity vector, cross delta x. And you know that any field that you can write as a constant vector cross the position vector field represents a rotation, right? So this here is clearly, this represents a rotation where the rotation vector is 1/2 omega.